Perfect. Floor is yours, Daniel. Thank you.
Okay, so hello everyone. My name is Daniel Lehenbauer, and this is my first time attending this user group. And so, thank you for inviting me. The thing I'm going to talk with you about today is my very amateur pet clone, and kind of specifically the story of how I kind of went from, not being a hardware designer. I'm a software engineer, but, limited understanding of electronics and hardware, to building this thing you see behind me, which is, it's pretty much a 4032 compatible pet. And here you see it's evolved from a breadboard to a manufactured PCB. And I'll tell you a little bit about how that happened. And so, not to go too far back in time, but the story starts with, my very first computer, which was a VIC-20. And I bought it at a garage sale for $9, and we took it home and it did not work. And my father, who is a field service engineer, was able to repair it. And it was kind of a big memorable moment. My dad was like a big hero when he did that. And I have lots of those, where I'd done dumb things to my computer, or something had broken in their toys and my father had fixed it. And one time I had my best friend over in high school. He brought his Amiga 500 monitor, and as he's carrying it back out to his car, he slipped on some ice and dropped it. And the weight of the flyback transformer sheared the PCB in half. And like in 15 minutes, my dad took the thing apart, glued the PCB back together, bridged all the traces, and had it working again. I mean, like what a hero moment, right? And so, so for me, when my son asked me, Daddy, do you think we could build a computer? I, started to get these ideas like, oh, maybe this is my moment. We could have, a special project that we did together that he's going to remember. And so I went on the CBM or the Pet CBM Enthusiast Facebook group and just kind of asked, a feasibility question, like, does anyone think that it'd be possible to build a pet on a breadboard? And it turns out it's something I didn't know about pet owners at the time, is that most of them own a pet because they fixed a pet. Like a lot of them have some knowledge of electronics because they've had to do repairs because these machines are, getting up to like 45 years old now. And so they're like, yeah, absolutely. And they started pointing me at like, Ben Eater videos and things like that. And so that kind of started my journey. The pet, it turns out, is a pretty good machine to do this with if you want to sort of, be a hobbyist and, build a very simple computer. It doesn't have a lot of requirements to boot into BASIC. There's no custom chips, just like no VIC chip or SID or anything like that. Actually, the chips that you need are still in production. And there's also designs out there that you can copy, like Glenn did a really nice clone of the pet that's using all modern parts. And so for me, I went even simpler than that. Like I just took a breadboard and put a 6502 on it, and then used a Raspberry Pi for everything else. And so the Raspberry Pi is going to emulate RAM, and then by putting data in the RAM, pre-populating, it's going to be my ROM. And it's going to, scan this memory address region, from, 8,000 to, 1K above that, and, display, the 40 by 25 character display, and so on. And the only thing that's kind of real at this point is, the 6502. And so I went ahead, did that, hooked it up, and I got this screen. And that wasn't quite sure what that was. I kind of remembered, actually, later in life did have a pet. I bought it for like $40 out of the classifieds because it came with a tape drive. And I used the tape drive with my VIC-20, but I had actually seen a pet before. So anyways, I'd seen that before. I kind of knew it was a machine language monitor, but I didn't know why I was entering the machine language monitor. And so I went back to the this pet CBM enthusiast group and told them about this. Like, oh yeah, there's this diagnostic pin that if you hold it low on boot, it'll cause you to enter the machine language monitor. And in order to send the right signal, you're going to have to emulate a little bit of the PIA chip. PIA is one of the I/O chips of the pet. And so I just did that, in C code on the Raspberry Pi. I said, hey, if it's asking for this, I will return this value, and it'll believe that the diagnostic pin is being held, low, and so, or sorry, not being held low, it's high. And so the boot will continue. And I got BASIC, which is pretty cool, except that there was no cursor. So I went back to the user group, or sorry, the Facebook group, and asked them, okay, I'm not getting a cursor blinking. Do I need an interrupt, or what's going on? And Janny Van Zyl on the group said, yeah, actually, there's the vertical sync sort of, routinely causes an interrupt, which causes the pet to like scan the keyboard and do lots of other maintenance things. And he suggests you should just fake it up. Like, you don't need actually the IO chips, just send a 60 hertz interrupt to the IRQ pin of the CPU. And so I did that, and look at that. We had a blinking cursor. That was pretty exciting, right? But I can't type anything. So then I learned about how the PET keyboard works, which is it's this matrix of switches, and you poke one value into the PIA to tell it which row of that keyboard you want to read. And then if they're holding down any of the buttons, you can read back, the columns on another port of the PIA chip. And so again, I just faked this up on my Raspberry Pi, writing a little bit of code. And after I did that, I also had to translate from, the Raspberry Pi. I've got a USB keyboard connected to it. I have to, do the PET matrix. And so at this point, I've employed a little bit of child labor to translate that matrix of switches into the right character codes and vice versa. And so that's my son working on that part of the project. And like all good Commodore users, we're using it on the floor of our bedroom, because we don't have a proper desk or anything for this project. And look at that. We actually can type in BASIC now and run real programs. And at that point, I was kind of thinking like, mission accomplished, we're done, right? So I was pretty happy with it. But during the process, my son had seen pictures of the actual PET 2001, and he really loved the chiclet keyboard. And this is where I realized we had a little bit of a difference in vision, because I thought it was a huge feature of my PET clone that, I had a standard keyboard with, all 4 cursor keys and so on. And he wanted, the real chiclet keyboard. And so our compromise was that I took a mechanical keyboard and had some custom keycaps made to make it look like a chiclet keyboard. And that's a separate project, and the URLs for that if anyone wants to do this. But anyways, we did that. But there's another thing that was bothering me, which is that with my very simple design with the Raspberry Pi emulating everything, the Raspberry Pi was the one who was toggling the clock signal up and down. And the Pi Zero is a 1-core machine. And so whenever I do something like service and interrupt, see if like, USB keystrokes or anything like that are happening, the software that was toggling the clock up and down, it would be suspended. And so you'd have this long period of time where no clocks happened, like long as in, a few milliseconds. But anyways, I wasn't actually getting a true 1 megahertz. And I was having trouble getting 1 megahertz, even if I got rid of like Linux and did like bare metal programming on the Pi. And so at that point, I decided taking a little bit another direction, which is to say, okay, let's use a hardware clock for the CPU and have it run at a true 1 megahertz. And in the diagram, you can see it's still being generated by the Raspberry Pi, but instead of toggling it up and down in software, the Raspberry Pi has hardware that can actually toggle it for you. So when the Raspberry Pi CPU gets busy, the clock keeps going at 1 megahertz. And so you don't have those long pauses like that. And I thought, okay, let's put a real, RAM chip on there so that as the CPU's, moving along, they can still, read and write to RAM. And so that was, the plan. And the idea is, and this is a design that Commodore's used to, some of their other machines. While the clock is, high, the CPU owns the bus, and when it's low, other chips on the system can, share the memory. And so you don't have to use dual ported memory. But in order to do that, I have to have something that's going to coordinate access, because now the Raspberry Pi is no longer synchronized with the CPU. And so I have to introduce a CPLD and in this protocol where the Raspberry Pi says, hey, I want to write something or read something. And the CPLD waits until the clock is in the right state, says, okay, it's your turn. And the CPLD does the access to memory and latches it. And then the Raspberry Pi sends a signal back to the Raspberry Pi saying, okay, I've got it. And then the Raspberry Pi can read it or write it. And so now we have a CPLD involved in this whole project. And this was a pretty bold step forward for me. It's like, before this, I'd like recapped a few Amigas, and, I could do some basic soldering and tinkering with an Arduino. But, now we're talking about like SMD components and manufacturing a PCB in order to get the CPLD that I wanted on there. And, Verilog programming, and we're working with signals at the 1 megahertz range, which, I'd never done before. And so, of course, that did not totally work. The machine, would boot into funny states. And this is one of the weird screens that I got, with, fractional bytes free. And I didn't actually know it was wrong. And I went onto some electronics forums and asked questions. They assumed I was competent because of the sort of questions I was asking. And so they were like, yo, check your signal integrity. Maybe the signals are ringing, or you have skew, or you've got ground loops. And I was going and researching all these things. But but my problem was actually much more basic. And it's hard to see from this timing diagram, but basically what it's saying is that when I turn off the bus for the CPU to let the Raspberry Pi access it, and then I flip it back on like this, there's a delay between when I re-enable the bus and when the data is actually settled and is available. And I wasn't doing that. I was basically turning the bus off and on along with the clock. And so I was, hitting the data as, it was coming back up to the right levels, but it wasn't quite reliable. And so once I figured that out, we actually had a working machine. But then my son had the same problem that I had when I first had my VIC-20, which is that I had no tape drive or disk drive or anything. And so we didn't have access to this library of games that, I was hoping that, we could learn from and inspire us to do fun things on the PET. And so we needed a way to load things. And so here, I thought this was just kind of cool. What I ended up doing was, writing some more code for the Raspberry Pi and saying I'll load program files, off of this SD card and basically DMA them into memory, suspending the CPU while I do it. And then I'll fix up a few basic pointers and, resume the CPU, and all of a sudden the program will be like instantly loaded. But with my first attempt, I didn't realize you had to fix up those basic variables. And so I get weird things like the program would load, but as I'd run it, it would corrupt itself. So I went back to my favorite Facebook group and asked some questions and learned how to do that. And then we had this. My son could hit a button and programs would instantly load. I mean, like really instant. It's kind of amazingly fast how fast a Raspberry Pi can put data into, this SRAM that's sitting on the breadboard. But then some of the, once we could actually load software, the fact that I was cheating without real IO chips and faking things up started to become more apparent. There's no sound. We didn't have upper and lower case. A lot of games would hang because they try to use the timers that are on the VIA chip. So by the way, the PET has basically two types of IO chips. They have the VIA and the PIA. And they have two PIAs and one VIA. And it turns out of those, the VIA seems to be the one that seems most important for games, because that's kind of where it became really noticeable that we're missing functionality. So at that point, I said, okay, we'll add a VIA to the design, and it's not too bad. The CPLD now has to have a couple more logic signals to activate the PIA when it's its turn to use the bus, but it just like these parts are made to work together, and so you just sort of add it and wire it up the right way, and it pretty much works except for these signals to select the right chip at the right time. Except for the fact that something I've been ignoring up to this fact is that up until this point is that the Raspberry Pi is using 3 volts, and the modern CMOS versions of these parts can also run at 3 volts. But if I wanted to do real I/O, I have to be running that at 5 volts, so that you can use like a user port and so on, which those are all at 5 volt. And so I have to add level shifters to the design. And so that's sort of the next iteration. But once I start adding level shifters and all of that, it's kind of like, well, if I'm going to add one IO chip, I might as well add them all. At which point I might as well just build, a real PET, sort of main board replacement. So I thought if I'm going to build a PET main board, I should go ahead and make it the right form factor and try to get everything right. And so I went back to the Facebook group, and they're super nice. Like Gavin Andrews, took out his main board and actually measured it to give me the dimensions so I could build a PCB that would actually fit into a real PET, if this board should ever be put into one. Chuck Hutchins explained to me how the power circuitry works, because there's this confusing part in the schematic where things leave the schematic and there's a capacitor and then power re-enters. That is really not obvious. He also was doing things like measuring the frequencies of signals so I could actually get the right timing for things. Sven Peterson, he explained to me kind of how much current the tape drive would draw by computing that from the data sheets for the transistors that Commodore used at the time. And we put all that together, and we come up to present day, which is the board that I have now. And so I'll stop sharing really quickly, and hopefully you'll be able to see me again.
I can see you.
Yeah.
Yes.
Okay. So the board here, it's kind of tethered, so I can't get it too close to the camera. But I'll take my unpopulated one here that I've sort of set most of the components in, and bring it a little bit closer so I can point out the kind of the main sections. So right here, this is all power along this edge. These chips right here, that's to do conversion to and from IEEE. IEEE is an interesting standard that, it's not 5 volts, it's like 3.4, with special requirements. Then here we've got, the 2 PIAs and the VIA chips. So we've got all the IO chips of the PET, and those go to the 2 data ports. Here's IEEE again, here's the user port. Then we've got a 6502, and we've got a RAM chip, and the RAM chip also doubles as a ROM chip. So on boot up the Raspberry Pi, basically copies the ROM into RAM. I've got 64K RAM, so I've got enough space for the ROM and the RAM there. Then here we've got the CPLD, which now is an FPGA. It's on a separate board here. I'll pull it out. So this is a dev board. I've made it so it fits in like this. And that's just because with the semiconductor shortage, it's hard to get these. And so I've been reusing them. And then the Raspberry Pi plugs in here. And now the Raspberry Pi, all it really does is provide USB keyboard and then video out. And so if everything else is done by the remainder of the system, and you can actually deactivate this after the PET's booted, and you can still hear music playing, you just can't, see anything. And so that's sort of the current state, and the state that I'm in right now is I sort of feel like, wow, this is a pretty complete and sort of a neat thing, but it's also not quite exactly a PET replacement, or sorry, like a mainboard replacement if you want to use it in a real PET. And so right now I'm working on doing the last little bit, which is to actually generate video and emulate the CRTC chip. So you could actually mount this in a real PET and use it instead of the main board if yours was damaged, or you wanted cool things like the instant load feature, or there's lots of other stuff you could do with this. And so that's sort of my project, and I can stop there and turn it over for questions.
All right. Now, I was going to say that board could be used as an emulator as well, because a lot of people are buying Amiga Forevers and, C64 Maxis and stuff like that. So it's a good product for the new market,
Mm-hmm.
those that never had a PET or something,
Yeah. So, I mean, that's the way I'm using it. Like, when we started down this, path with my son, I was thinking this is like a $20 project. And now I'm up to about, it's probably at a, more like 120 amortized to build one of these. But, when you get a PCB manufactured, you have to buy 5 of them at a time and so on. But I'm still coming in quite a bit lower than buying an actual PET off of eBay, because they're rare vintage items. And so it's like, you're looking at like 1,000 for a, kind of a nice one, obviously. And then, maybe you can get a broken one for like 500 to 600 or something like that. So yeah, if anyone wants to tinker with a PET, it's certainly a good option.
You did a good job, man, with the presentation. I like the PET that you made there.
Oh, well, thank you.
I have a quick question. I mean, have you considered, lowering down the number of cycles per second? So like not 1 megahertz, but lower, and use this as a kind of debugger, but hardware debugger. Like
so
stepping code, for example.
Yeah, I haven't done it intentionally, but I did. I did clock it lower while I was working on it at times, just because it was helpful for debugging it. And what was really cool is while it was synchronous with the Raspberry Pi, moving the clock up and down, with software, it was sort of like a systems, like you debug with JTAG on modern machines, where I could like single step the CPU and like check all the lines and so on. And so yeah. It could be useful for that too, if someone really wanted to get into PET software development.
Yeah, cool, thanks.
Mm-hmm.
Very impressive. How long did it take you to do it?
Oh, so it's been just a little bit over a year since we started. And it's been sort of intermittent investment as my son's been interested in it or I've been interested in it. So I'm guessing, I probably have, in man years, like 3 or 4 weeks of, like my time dedicated to it at this point. And a lot of that was learning and watching YouTube videos about Verilog and things like that to, learn all the different skills to be able to do this.
Does that PET does that go online, or I saw it has an IEC serial bus, or not too sure what that is on the left far side.
Yeah, the IEEE. Yeah, so the IEEE is a standard. And so some people are use it to like, interface to modems and serial devices and so on. Some people do it with the user port. So you've got a couple of options. There's the one that I'm using here. I'm actually using an interesting device, which is, it emulates the PET's disk drive, but it's also connected to Wi-Fi. And so your disks can be on the internet. And so it's sort of like an instant BBS experience where you can actually go and list the directories of other people's, like website. It's like a website that's hosting the files, but you can like list their directories and load their programs without ever transferring them to your machine, which is
that's awesome.
Yeah,
that's awesome.
like I think it's a lot of fun.
I'm not familiar with the original graphics chip on the PET, but how do you handle the video and graphics? I know it goes to the Pi, but
yeah. So the PET didn't really have any. So it only had the 40 by 25 display, and then you had PETSCI. And so when you see these programs running in the background, like that's just PETSCI that they're using to make the graphics.
I see. Thank you.
Really nice, thanks. I don't see more questions. I see in the chat a lot of comments. Actually, there's one just coming. How much current is the circuit board pulling?
Funny you should ask, because I had a few missteps where I didn't allow for enough current. So I think right now I'm getting close to, well, that's not true. I think it runs probably like 500 milliamps or something like that. I don't think it's terribly a lot, except for this keyboard. This keyboard has a wireless feature. And so when you first plug it in, it starts charging. And I didn't realize that was going to draw a lot of current. And so like in my first, earliest designs with the PCBs, the voltage regulators were like smoking and things like that as my keyboard was charging itself. So it took me a while to figure that out. So now it's, the power section is actually rated for about 3 amps.
Okay, thanks. Really cool.
Yep.
Good. Thanks a lot. I don't see more questions. I think you provided me a link today, but I will post it on the website. But you can maybe also post it here in the chat. Also, if people have more questions, they can probably use the chat as well. I will now stop the recording. Thanks a lot again.